Welcome to part 3 of building an avionics flight simulator hardware interface with the STM32H723ZGT6 microcontroller. This is a continuation from the previous videos, so let's go ahead and get this going. We now have the generated code, and I'll go ahead and make some changes right now and just do a test to make sure that the code we generated is running and working. So let's go up and going to add some. Okay. Actually, I'm going to go ahead and define this here at the top. We only are using one channel, so this is the number of ADC channels variable, and yeah, I'm not using any notation just to get it going right now. So this would be used here to give an array. Right now it's only 1, and we're initializing the value to 0 in the ADC. Okay, so let's go over a few of these variables, private variables that I define. I use volatile to make sure that the compiler knows not to optimize this variable, so it will always change and report the change in variables. So because this will change very frequent. And this timer to count, this variable will store the counting value that I'm incrementing as the timer is counting, and for timer 2 and timer 3. And this is being used to change the incremental value. So what if you're counting up, it will give a +1. If you're counting down, it will give a -1 value. And this is being used throughout, and I'll show you where that will be used. And I'm going to add that code right now, but at least we're going to use these variables to take care of that. Additionally, there are certain conditions in transition where the value, you're determining whether or not it is plus or minus, but there's certain conditions where it will just return a 0 in that condition. So let's move on. So in the other locations, I didn't go over, for example, certain drivers are included. And this is in the folder drivers, CMSIS, under device, ST, and you have these files, but we're not going to reference that yet. We don't need to, but what we will eventually use is in the HAL driver. This contains a lot of the drivers for the ADC. This is the header file. Let's go into the C files for now. So if you can see, there's the ADC, the DMA. This is for your external interrupt flash, and then your GPIO. And what else are we going to use? Yes, the RCC, the timer. So in these, we're going to find some methods that we're going to use eventually. So notice you can see the HAL timer base start and stop. Eventually these will be called, but most of them we don't have to worry about for now for what we're going to do. But I'll go through the ones that we need and let you know there's certain callback functions that we're also going to actually override. Overriding those will allow us to customize it. This one would be, we're going to use this for the update event. So remember we did a timer 15. This will be the update event. We're going to override this. And there's certain, the encoder ones, we're definitely going to use this. We're going to use to start the interrupt. And this is not a callback function. This is something we're going to just include in the main to start the interrupt. And let's go and see. And also in the ADC driver, HAL ADC, there's another one that we're going to also use. That's called the HAL ADC convert complete. Okay, this is a callback one we're going to use. It's defined as weak, so that means that we can override this. But we're going to at least have to put it in our code. That one we can copy and paste. And for right now, let's go ahead and just copy and paste this one in the main. So we're going to take this to the main. I just wanted to show you that. The rest I'll just paste from previous use and just show you how it's working. Let's go ahead and do that. Let's paste it here. And right here, we can just delete everything in it because it can be empty right now. And from there, let's just check a few other things. Okay, let's go back to the ADC driver real quickly. And in here, there's a HAL ADC Start DMA. We're using a DMA we already configured the DMA. So let's go ahead and use this right now because we're going to need to get this started. Let's copy the signature and right below in main, and we're going to take this over to the main file, and right below right in here, gonna make a change real quickly. What we're going to do is, since we're using the ADC, we're going to pass in that variable to the ADC, and that is ADC3. We are going to pass in the buffer. Remember, we defined this buffer here. That's the value we defined. And we're going to replace it here, right here. That's just a pointer, and we need to basically, and then the other thing we're going to add is the length. Right now it's 1, but there it is. So we cast it to a 32-bit array, and it's only length 1, but in the future we'll change that as needed. So as we add more potentiometers, we'll change the number of channels so we can capture that. So this is basically going to start it so you can see the value and the buffer that it will be updating for the ADC. So we can look at that later. Okay, so let's go back into the HAL timer driver file, and we're going to look at one of the ones. We're going to look at the timer encoder start interrupt. This is the one we're going to utilize, and this is going to start the interrupt based on the timer you're using and the channels. We're going to define all channels. It tells you what parameters you can use. We're going to use all channels and then the timer that we want. So let's go back over into the main file. Just going to paste it from my code right here. So there it is. So we have HAL underscore timer encoder start interrupt. It's timer 2, and it's going to start all channels. So we only have 2 channels that we defined for this one because of the encoder. In encoder mode, it's using channel 1 and 2. So, and the same. So in that case, that will be the rest. And there's one other one that I mentioned that we're going to do as well. And if you look into the base timer, so there's just a regular interrupt for the base timer. So we'll start that. Let's start that later. But for right now, we started an interrupt, but there's some other things I need to do before we start the interrupt. Before I run the code. There's some other things I need to do before I run the code. But we can go ahead and at least put this over for now. So let's do this real quick. Okay, for timer 15, we're going to start an interrupt on that as well eventually. So let's just put that there. So those are the interrupts we're going to use. And for right now, except for the GPIO that will already have running, that's already being started. So I'll ignore that for now. And okay, there's some other methods or functions I need to bring over. I'm just going to add them here. So I have one that will do a count. So let's just add that there. You're not going to need that. And that will basically count the values. I'm passing over a value that's coming in, and it's incrementing the pointer that I'm based on whatever the incremental value is, whether it's -1, whether it's -1 or +1, or if it's just 0, it does nothing, but at least it's passing the pointer. And then there's a bitmap that might not be using this anymore, but I left it there for now. I'll address that. So the next method I'm going to add is going to be the one that eventually we'll call the do count. So it's doing the count here. At first I was using this to disable the bit, but I found that it was best to do it in another location. What's happening here, as it's coming in, I'm recording the count from the encoder. And then this value coming in that's being passed in is actually the previous count number. So if the new count number changes relative to this, if it's greater than or less than, then it would determine which logic to apply. So this logic basically is the one that determines whether you're counting up or down based on what the encoder is doing. I had a range for this. That's because during testing I noticed some issues where it wasn't always sequential based on which counter value I was getting from. I didn't want to put a fixed counter range. That way, if I changed the counter value in our code before, when we configured it to count up to 255. But you can configure the encoder to count more than that. So I left that there for now. This handles if you're counting from, let's say, if you're at 0, you won't go negative, but it will count up to basically the maximum. So this handles that, and this does the reverse, and this will do from 25 to 0, 255 to 0. So that's a special case when you're counting from 0 or counting ascending and then all of a sudden it starts over. So this handles that condition, and this is a regular condition. And if there's any other condition else, then it shouldn't do anything else. This is the value that it determines. Well, if it's not 0, then you need to update the encoder. At this point, it will do that, but you also need to update the relevant bit. And that is something I will show you in a bit. The next method I'm using will eventually go here. Let's add that here. So all this does, I'm using a variable, and actually at this point, let's just add it to the code. I created a separate header with a special declaration for a structure that I'm using for my case, and I'll just share that. Okay, so here's the header. I'm gonna put it in the includes folder, and so I named this HID underscore Avionics underscore interface. The special structure that I defined that I am using, or map the structure similar to the HID descriptor. So that's the structure that's being sent back over to the USB interface. So this is a structure. This is the first part, is 16 bits, and this defines it as 1 bit. So each one of these represents 1 bit. And for encoder 0, it's up or down. So remember in the previous video, I showed that if you're counting upwards, it will hit the 0 bit or the lower bit. And if you are counting down, it will trigger the second bit. So for this would cover one encoder, encoder 0. This will cover encoder 2, or the second encoder, and so forth. So encoder 1 and so forth. So each encoder utilizes 2 bits. So whether you're counting up or you're counting down. This is an array of 8 bytes, and these are the encoder values. So the encoders will count up to 255, and I'm passing those over as well. And then the second structure within the structure is different button. So I'm utilizing 14 in the one that I demoed in the introduction video. But for right now, we're going to use the first 4, and I'll just double check. I'll map them to correlate to how I did it in the demo, but for right now, yep. So that's what I'm using it for. And so there's 16 different buttons here, and there's a value for the var knob. So basically, potentiometer will utilize this value at some point, and likewise, I'm actually utilizing this to return data from the computer or from the simulator, and these are output. So that is actually working, but we'll discuss that later. But notice when you declare these, or you define this structure, the attribute packed, when you use this, it makes sure that there's no bytes that are in between each structure. So it compacts it. So therefore this should give me a total of 20 bytes, and there's no padding bytes in between. So it removes any padding bytes. So if you're looking for, let's say, byte 0, which would be byte 1, which would be if you're indexing by the 0 index, this would only give you up to the first 8 bits. The second byte will give you the next 8, and so forth. And you keep going up. So based on that structure, we're also going to convert this structure into a pointer array alias, so we can pass the structure over in an array format. So we'll discuss that later. But I just wanted to explain what this means. This is certain definitions that I was using for the bit correspondence, so you could map them. So I just wanted to show you I'm using this because I defined it, so you understand what it is. So we could continue on. So from here, let's just make sure I have everything that we need to just give a basic demo right now. So this set up and down method that I just copied over, I'm using this based on the bit map that comes over. It will determine if it's which one of the encoder and what action is being done, whether it's triggering up or down. And it goes all the way down to 8 encoders. Encoder 7, because we're starting with a 0 index, is reserved right now. We're not really using that. And then if nothing else, it just exit out. That's what I'm using to actually update bit flag in my structure that I just showed you here and the header file. So this will determine that. So let's go ahead and close that and make sure we have everything ready. So the next thing, I'll go back to the encoder increment method. This is what I'm using to do the increment logic based on what the encoder is doing. I went over the first section. So this second portion, I just use this this here to make sure that, one, I wanted to get the bitmap. So I wanted to determine based on the value coming in from this timer increment value. So we set it up here, whether it is +1 or -1, it determines the value here. Notice that if it's 0, it's not going to come in here. But if it's either -1 or 1, it's going to determine which bitmap to use, whether it's the up or down bit. So based on that, I'm using that to set the up-down active with the bitmap, and then do the count as needed. So from that, if I was to set it inactive, I used to do it here, but on debugging, it wasn't the best place to do it. And I'll explain why I did it the other location later. All right, so I have to bring over some more variables. These are the variables that I'm going to use to determine the buffer. So let's go back into the interface file. So if you notice, the first part of the structure is input, meaning we're sending that into the USB HID. So if you were to count all these bits and all these byte structures, they'll amount to 13 bytes. And then these for the output will amount to 7 bytes. So if you look here, this buffer interface for the HID avionics interface descriptor structure, when I declare this, when I'm only sending 13 bytes. So this creates a pointer to this structure, and it will go through and actually convert. I'll show you where I convert it. Eventually, I'll convert it to pointer. It will just be an alias to this address. And then I'm only going to use 13 bytes. So this just clears the number of bytes that will be sent over. So it's just going to be like an array. So once you declare this pointer, it's going to work as an array, but it's just going to be an alias to this address right here. So it's going to have the same address starting point, and then you can increment up to 13 bytes to get the first part of the structure to send over. So, all right, so we'll just move on from here. So let's check down here real quickly. So we just included this. This was one of the count values that I had declared above, and probably should have this outside, but for right now, let's just leave it there. Just wanted to make sure I have everything in order. I'm going to try to just do a compile real quick to make sure that nothing breaks. So I'm starting the timer, and there's one section I need to do. So once this starts, okay. So I need to do another callback. Actually, let's see if it's ADC callback increment. Okay, I see the callback that I need to include. Okay, so I'm pasting it here. So this is the callback method that I'm using. It's taking a pointer to the timer, but based on if it's timer 2, it will increment the timer 2 value. And if it's timer 3, it will increment timer 3. So as you turn, the input capture or interrupt will trigger. So when you turn any one of the encoders, it will trigger this callback. And then based on that, I'm determining if it's timer 2 or timer 3. It will determine which one of the encoders is triggering the callback. And based on that, it will increment that specific encoder. So this is the code I'm using to do that. So hopefully that will help anyone trying to figure this out. And I'll do some more testing in a minute. There's another method I have to include, and this is a HAL delay included in the library. You have to include this, so I'm just overriding it and including this ink tick. If you don't do it, then it just gets stuck in an infinite loop because it's not incrementing the value. So I just had to modify it and override it. So just so you know, that's an issue. All right, so there's one more update I have to do in the HAL ADC capture. Based on the value of the varnub ADC data, when you turn the variable resistor, it's going to return a value. Because I'm using a 10-bit, it goes up to 1023. Okay, so I'm using this section right here to convert the ADC buffer value to a maximum of 255. Because it's 8 bits, it goes up to 255. But there's also a gotcha with the variable resistor that I'm using. It's supposed to go down to 0, but it never does. The minimum value is about 28. So I have to adjust for it and scale from 28 all the way up to, or 1023 as the maximum value. So this basically converts the value so that I can save it in a 255 max 8-bit value. And I'll show you what I'm talking about. If you look at this potentiometer here, for some reason, when I turn it to the minimum value, it is only going down to 28, about 28. So I just wanted to fix that in the code. But this is probably just a bad potentiometer. I can change, but it should go all the way down to 0. From 0 to 1023 at the max. Right, we're going to go ahead and make one more change. I'm just making sure there's nothing else, just before I do a quick test. There's nothing else to fix in this. Let's go on to make sure everything else is ready to go. Okay, there's something else I want to show you. If we look at the GPIO, open the declaration, notice this is where they're enabling each port we're using. We're using port F, H, A, D, and B right now. And as we define pins, we had defined EF6, 7, and 8, and we did it pull up and falling, and we enabled the interrupt here. So just wanted to check because sometimes they might not come in properly. I just wanted to verify that those are set up. So it's going to set the priority. The one thing I forgot to do is for this to work well, I need to change the priority to 4. I mean, less than 0, because update event is going to run on 0 and all the other interrupts, they're on a lower priority. So bear in mind, I could have done that when I configured the microprocessor. Now that I have this priority updated, I'll go ahead and include one more callback. So this is for the GPIO External Interrupt. So let's go ahead and add that in. Most of this code at the bottom, these were generated by the OGen in the STM32H723ZGT6 environment with the initialization code. So there's one more I need to include here, and this would be for here. There we go. So relevant to what we activated. So I activated pin 15, 8, 11 for interrupt. That is, this is for pin 6, 7, and 8. Yeah, we included that. So this would be for encoder knob 1 button press, and this will be for 4 buttons that will be on the board. So just so you know, that's what this is basically doing. As you press it, when you first press, it will trigger this interrupt and it will turn it on. And then if you're still pressing, it will stay in this while loop. From here, this also helps with the debounce as well. So this is a nice way to handle your debounce in code. So if you're still pressing, it will stay lit or activated. And as soon as you let go, it will continue on. So this is only for button events. So when you do this, it will get that triggered, and then it will reset the button in the structure here. So at this point, if you look here, these are the button events. So if any one of these buttons are pressed, it will do that. I just wanted to check real quick and just make sure that I have everything. And if you can see here, let's turn this on so you can see the board. Again, this is the encoder we're going to use. We have 2 channels, channel 1, channel 2, and then the button. And then we activated these buttons here. So that's what we're going to test real quick. If you notice here, this is the dongle. This is the ST-Link that programs the board itself. It's connected here. So this will program the board and write the code that we just generated, plus the modifications I made to it. Let's save, and let's make this a little bit more presentable. Okay. So there we go. So these 4 buttons for encoder 1 and 2, which is the knob 1. The knob 1 has 2 encoders, so channel 1 and 2. These are what will be triggered or activated in the structure. This the ADC value will change this value, and then the buttons will be here, right? So let's check out our connection. I wanted to show you this because it will ask you to configure it. So before I just wanted to show you that this needs to be connected, and then we can move on. So let's go ahead and turn off that for a minute, and let's run the first thing. I want to clean the project. Let's clean it. Should be fine, but start build immediately, and we're gonna build only the selected projects here. So go ahead and do that. Chances are it will probably throw 1 error or so, since this is the first time. Oh, yep, that would help. So what I needed to do was to, I didn't include the header file. I'll go ahead and add the header file for this is for my header, the one I created for the Avionics structure, or the HID structure. So I needed to add it. So I'll add it right here. With this, hopefully that resolves all those issues. So go ahead and clean it. Okay, there are less errors now. So let's see which one. This one is, okay. Yeah, I changed it. So this should be this value. Buffer ADC. Let's change that value right there. And let's go ahead and do it one more time. And then we're down to 2 more undeclared. Let's get that over there. It turns out I wasn't using this anywhere else, it seems. So I was using it earlier in a previous modification that I had from one of my code I copied over. So let's go ahead and try it again. Clean. All right, so we have no errors. So we're going to go ahead and debug. So it's gonna pop up the interface. So I'm just gonna show you the first time you're running it, it's gonna pop up because it didn't recognize the ST-Link. So if you go into the debugger, we're using the ST-Link, and we are gonna select it here. Let's scan. And there it is. And that should be it. We shouldn't have to do anything else. It picked up the debugger here, and we're going to apply and click OK. Let it debug. Okay, so it normally stops at the first line of code. So from here, we can go ahead and test and see if everything is working. We're going to add some live variables later on. Some are already there, but let's go ahead and see. All right. So for right now, seems to be running without any issue. So let's see if I can see the buffer. So this is the encoder. This should show me any bits that are, so remember, so let's go ahead and turn on the camera so you can see. So if I'm turning this, this is the encoder. There it is. So, okay. So notice it's not resetting. Remember I told you I had to change where I reset that value. So that's good. 2 good things. It's working, at least for what I expect, but I'll fix that real quick. Here, if the buttons that we activated, we press button 0, these were all activated. These are working. You can see as I hold it, it will stay on, still working, working. Bingo. So those 4 buttons that I programmed, the interrupt is working. And if I do a breakpoint into the interrupt, you can see it's triggering within the interrupt. So let's see if I press the button as well. Yep. So when I press the encoder knob 1 button, it should stop there. There it is. So I put a breakpoint there, so I could continue. So that's the encoder button, and we don't need to do all, but I'll just put button 1. So, and if I do button 1 up in here, oh, I didn't continue. Yep. So I pressed button 1, it came in. So continue. Yeah, we can take these breakpoints off. So you can see on the right side again, as I'm pressing these, you can see the values are changing in yellow. If the value change, you'll see it in yellow. Yellow as I'm pressing. So that's the interrupt. So the interrupt is working. So we were able to go through and start up the microprocessor with the STM32 Cube MX. And we were able to get that up and running with the interrupts working. The ADC, let's just fix that real quick. Oh, let's check the ADC value. That should be working. So as we, that's the timer. It's not what I want. The port buffer, and yeah. So the ADC seems to be working because it's showing a value there. So if you look, I'm going to change the value from the ADC knob, and it should start. Well, it took the. Did I stop the code? No, didn't. Am I not updating that? Let's see which other value is coming. It's taking it from. Okay. Let's do one more thing here. This buffer ADC. Let's just add this value here. See if it is showing anything in the buffer. Yeah. There's a value in there, but it's not the value I'm looking for. So let's see if it's even coming in. I can check that out later, but let's do a quick check. Oh. Okay, look like I found what's happening in the ADC. It looked like it doesn't have a continuous conversion mode on. So I'm going to see if I added it or not. Hold on. So that was strange. I'm pretty sure. I thought I did continuous conversion. Oh yeah, that was my fault. Continuous, it was not enabled. So I'm not going to generate any code, but I'll save it for now and enable it manually. So let's close this. So I have to hit enable. I have to enable this right here. So that should fix it. So yeah, those are some of the bugs. So, and especially I didn't cover that. So that's what should be enabled. Yeah, let's go ahead and try this. All right. So, okay, now the breakpoint is hit. So it is working. So, yep, because that is changing all the time and it's changing rapidly. So that's why we needed to put that as DMA, direct memory access, because you don't want the processor to be dealing with that every time because it would take up so much resource. So let's see. So if we look at these variables again, you can definitely see in the buffer here, it is changing. So that's a good thing. So if I go ahead and changed. Oh, wow. I actually, I had the camera on, so you weren't seeing what I was seeing. So maybe let's go back down. If you didn't see that, that's important. So let's go back to the ADC. So I had to enable here continuous conversion mode. So yep, that's what I had to do. So just so you see, that's what was going on. So I forgot to disable the camera. So let's go ahead and enable the camera real quickly. And if you look to the right where the yellow values are, as I'm turning the potentiometer, goes up and then it goes to that minimum value somewhere around there. And then we're going to look at in the report buffer that we're building. So you can see the knob there. It's changing. But yeah, if we go all the way up, there it is. It maxes 255. It will go 216. Yep. And so those values, and in the buffer value here, it is stuck on that. I might need to figure out, change something else because it looked like it's going down to 27, but as the minimum instead of 28. But for right now, that fixes the issue for us. So perfect. So your ADC is working, and can change that value, and it's changing. If you look at the encoder, yeah, I still need to do the encoder fix and to reset the value. If you look at the buttons, the button bitmap structure, if I press it, it's working. So let's fix that real quickly. Okay, so let's go here. Okay, so the next thing we needed to do was to include one more callback function, and this is for the timer. Timer 15 we had defined as the update event. So we need to make sure we include that, and there's something I need to add here. And I need to do some, just make sure I have the correct variables there, because there is a part of it that requires me to update some values. Yeah, so let's go ahead and do that. So let's add it here. So these variables, like let's say you're pressing a button event, if you're not sending them values repeatedly, at least 10-20 milliseconds, it's going so fast that it won't register as a trigger event on the avionics, or for you even to recognize that it's even updating. It's going so fast. So I define the max, for example, count before it resets. So it will go through like 200 attempts first before it resets on certain values. And I'll figure out probably a better way to do it. But for right now, I was using that as a way to get it done. Right above here, we'll just go ahead and do it right here. So perfect. When we're calling the report, we're going to send it here. But for right now, let's change this to toggle. I think there's a toggle one. So let's open the declaration, make sure have the toggle pin. So we're going to toggle this pin, and we're probably just going to delay just to show you what's going on. I could do it in a loop, but the best way to do it is with the update event here. So we're just going to use a toggle pin. We didn't define that pin. So pin 7 on port G corresponds to, there's a blue light here that I'm going to show you. There's a LED on the board. I keep forgetting to turn off the camera. So what I did, if you didn't see what I just did, I added this callback, and this is every time the timer ends the period, it counts to a specified period that we gave it. It will run this callback method. So once it runs, it should toggle this pin, but we didn't define port G, I don't think. So I'm going to check the GPIO settings to make sure we have it defined or declared or enabled. And from there, I might be able to manually do it here. So that's a good learning experience if you want to see how it's done. So let's look at the camera real quick. So there's a blue LED light here. So it's supposed to toggle that one. That's what it's going to do on the board, just to show you that it's running. And then eventually this is where we would actually send the USB report that we have, but we have to configure that with a few more settings. So that will be in the next video. But for now, let's go ahead and do this. So let's first check that we can set up port G. We didn't have port G, so we're going to enable port G. So we enabled it, and since we enable it, we're going to go ahead and configure the output. And then we're going to configure the pin. And this is where I'm using this section to configure the pin right here. So pin 7, we want it to be output, and we're gonna pull up right now, and let's go ahead. This one is not using an interrupt, so we don't have to worry about setting the priority or anything of that sort, because this is also an output, not an input, and we didn't set up any interrupt for it. So let's just make sure we have everything done for that. All right, so I think that should fix our issue here. Port G should be ready in 7, and then that will trigger that LED on the board. This is basically where we were updating our data. And now that we have that, we need to add something else, because remember earlier I discussed this pointer. Because we're going to configure this, we basically use the address from this HID Avionics interface struct that I defined. And I'm putting the address, and in the structure, I'm only going to need the first 13 bytes. So this just gives the length of the bytes that we're going to send from that structure in this structure variable that we define. So just wanted to show you that. We're going to go here to actually create an alias to that pointer right here. All right, so we're going to basically right here got the address for the buffer data or structure that we're using. So it's the HID Avionics interface descriptor structure. So I'm just getting the address to it and convert it into a pointer of 8 bits array, so that we can now reference that. And now we can use that to update the value here. So every time this will reset those values. So remember, we didn't reset the values here anymore in this code once we were doing the increment. So we didn't want to increment it here anymore. I want to do it on the timer, and the timer will do it synchronously with everything else we're working with. So I wanted those bits to be updated at that point. You want to check a few things. Yep, good. Probably want to delay a little bit so you can see it. Let's try it without. It's probably just going to be bright or just, yeah. So let's just copy that. Let's debug it and, cancel. So right here, do I have it here? Oh yeah, I have it twice. Let's clean it first. Clean. And I keep forgetting to disable this camera. Sorry. All right, so let's go ahead and run it. My apology for that. I keep leaving that camera on. Okay, so this is the line of code I added just in case that I blocked it with a camera accidentally. I had to initialize this pointer with the address for the report buffer from the Avionics, the HID Avionics structure we defined, so it can convert it to like an array format, the byte structure. So let's continue. All right, so it's running. Let's go to the live expression. This looks like it's working, right? So our ADC is working. Perfect. Let's go into the buffer. And now it should be updated. The encoder values should update. So if I turn it, yep, they're resetting. Notice you'll see it's incrementing up. If I turn it down, it's incrementing right. Perfect. And then it works. So this is the channel 1 and channel 2. So if I turn it up, it does the incremental bit. If I turn it down, it shows the decremental bit, and vice versa. So that's how it should work. It's working perfectly. And if you look at this array of structure, you can see the value is counting here. So in encoder 1, as I turn it up, it is showing that, and we'll send that over. We're not currently using that in the HID descriptor, but on the other side in the cockpit, but at least you can see it works. So this is encoder 2, the second channel. As I turn it, it counts, and then it shows the incrementing values at the same time. So but let's just show you again with the camera on this time. So as I'm turning encoder 1, encoder 2, so it's going up, it's showing the incremental bit being triggered. Going down, it shows the incremental bit being triggered. And likewise, this second encoder, up, incremental bit, down, it's the bit. So that's working. So that also shows that this is automatically triggering. So if you notice, the LED is triggered on as well, the blue light. So we can delay that. We'll put in a delay so you can see it much more. It will be much more visible here. So let's stop. Let's turn off the camera for a minute. And just, I don't know if the delay is enough for you to see it blinking, but we'll just add a value to it. So now you can see it blinking on the camera. So let's turn back on the camera. You can see the value blinking here. You can see the LED blinking right there. So with the delay, that kind of slows it down for you to see it. So there it is. So we're gonna leave it right here. So we were able to walk through from scratch. We were able to configure the microprocessor with the STM32Cube application from STM, and we were able to enable interrupt. We were enable the timers, encoders. So we did the encoder timer and we did the update event timer. And so let's turn off the camera. So we just review a few things here. And as you can see, we were able to do the conversion complete callback that updates the data for the ADC. And yep, so that's the overall basic setup. So the next time we'll go into the USB HID structure and what we need to do to get it working from here. So I really appreciate you taking the time, and thank you very much again. Now that we have completed these steps, in the next video we'll go over the HID descriptor, and we'll go over the other configuration to start sending and receiving information from the computer via the USB HID. Thank you.